This is a presentation on a checkers implementation that utilizes the alpha-beta algorithm for building a smart checkers opponent. To begin, I'd like to describe the alpha-beta algorithm. Alpha-beta pruning is an optimization on Minimax where the algorithm prunes branches it knows cannot contain acceptable values. It determines this by comparing the value of the parent node to the calculated child node. This is best understood by way of a picture. As seen, each depth level corresponds to a minimizing layer or maximizing. In my implementation, the maximizing player is the computer, since it utilizes the algorithm for determining a move, and the minimizing player is the human. The tree is evaluated in modified post order. It is modified since after each evaluation, it compares to the parent to see if the branches can be pruned. In this example, the minimum of 3 and 17 is 3, which is then propagated to the parent, and then the right child. 2 is then compared to the propagated 3, and 2 is found to be smaller. 2 at location 5 is compared to the root at location 4. Since the minimized 2 will never succeed the maximized 3, the right branch can be pruned. In this example, the benefit is minimal, but for a deep search, this can save many evaluations. This is implemented in the alpha-beta CPP class. The best successor state AB algorithm starts by initializing the alpha score to a minimum, then gets all the successor states. It then evaluates each of the successors. To do this, it calculates the next move the user will take, assuming the human player takes the most optimal play, according to the built alpha-beta trees. Finally, it takes the maximizing score of all evaluations and returns that. The min and max value functions are very similar. The main difference is that the max evaluates for the largest possible alpha, and min the smallest possible beta. Note that this heuristic is only evaluated once the leaf nodes are reached, as seen in the if max depth statements. Next we look at the successor states function. This function is responsible for calculating the possible moves a player can take. Depending on the supplied player color, it will only evaluate that player's pieces, since a player cannot move another pieces directly. The first if statement handles determining how to set the loop to evaluate pieces. The human player's pieces are 1 to 12, and the computer's are 13 to 24. We can then evaluate the moves possible for each piece. We first check that the piece is not eliminated, which is stored by the game in the piece location, or PL data structure, as a -1. If the piece exists, then we check for valid moves in all directions. This relies on a call to the game called isMoveValid, which returns a supplied move is valid. If it is, we create a copy of the in-progress game state and commit the move to this newly created game and add it to the vector to return to the caller. Finally, we look at the heuristic function. This function is simplistic in its calculation, and is responsible for returning the score of the current board to a caller. It looks at 3 different aspects of the game: the number of pieces a player has, attributing a higher value to royalty pieces, the closeness to earning a royalty piece, and the Manhattan distance of a king from the nearest enemy. The calculation for the computer player adds to the heuristic value, while subtracting for the human player. The way this heuristic is constructed yields a very defensive and frankly stupid opponent. A way to alleviate this is to pre-compute some opening strategies to help start the game, since the algorithm really struggles with openings and closings, but I could not implement this in time. Next, we look at the implementation of the game. The game itself is a struct containing the data for a given game state, including the board, the location of pieces, the number of pieces remaining for each player, a heuristic value holder, and the last move that was taken. Looking at the data members, we see that a piece is simply an int that represents a specific piece. A board is an 8x8 array that stores the locations of pieces, and piece locations, which is a different way of storing pieces. This double representation uses more space than required. Initially, I was only to use a 4x4 board that represented all the playable locations of the board, but this would require a scan each time I needed to find a piece, so piece locations was added. I then realized it would be challenging to do moves, since I would have to keep track of how a move should update the underlying 4x4 board. I deemed this to be too complicated for the space saved under the time constraint, so I opted for 8x8. This is a definite spot where additional optimization is recommended, since this would halve the space required for each board. The game.hpp file declares several functions used for transforming boards, as well as helper functions for maintaining them. The main functions, in the order they are often used, are isMoveValid, commitMove, removePiece, and isNextAttack. The helper functions include getPieceColor, getPLXPLY, which is an inline, isEnemies, isGameEnd, printGameBoard, and printPiece. Finally, the game can be installed, and the demo runs through a preset move list. Since no randomization was implemented, games are deterministic. After the demo is run, you can scroll up and see the moves the player and the computer ran. You can also play against the computer by navigating into bin and running checkers easy, medium, or hard. The CLI will instruct you on how to play, and you can experiment against playing against the different difficulties. Have fun!